So for capital budgeting from chapter 12, I decided to solve question 3 of practice questions. Question 3 of practice questions from chapter 12, integer and linear optimization model. So in this question, and in capital budgeting type of problems, we usually have a list of projects. And then we just need to select among them. So our decisions would be whether we want to take project 1 or not, whether or not we want project 2, whether or not we would like to take project 3 or not, and then the same thing for all of them. And usually we have a capital fund available, like we have a limit. So this actually is a classic constraint that we have to face, the amount of capital available. So we won't be able to, for example, invest more than 10,500 in year 1. So we have to make sure that we take the right set of investment such that we don't use any we stay in our budget available in that windows that we have, and then we also want to make sure that we get the maximum net present value, so maximum NPV. So that's our objective. So in this example, in question 3, we have a list of 6 projects. So let me just go here and write it down here. So decision variables. So the decisions that we want to make, whether or not to invest in project I, for example. And let me denote this decision with xi, where I can be 1 to all the way to 6, because we had 6 projects, right? So we want to develop an integer programming model for maximizing the net present value. So our objective then would be, and then I said whether or not. This means that xi's can take either 1 or 0. 1 means that if project I is taken, if project I is taken, otherwise. And then objective function, we want to maximize z, or maximize let me just, instead of z, let me just put NPV, net present value, which is, so if we invest in project 1, which is limited warehouse expansion, if we invest in this project, at the end we're gonna get 4,000 net present value. So that's the current equivalent value of the project at time 0. So we don't care about the cash flow, but then this is the value of the project right now. So we're gonna get 4,000. So we get 4,000 if we invest in this project. So our NPV would be 4,000 if we invest in project 1 plus, so if x1 takes 1, we get this NPV. If x1 gets 0, we don't get this one. And then 6,000 x2, sorry, 6,000 x2 plus 10,500 x3 plus 4,000 x4 plus 8,000 x5 plus 3,000 x6. So that's the objective function. That's the total NPV of our investment. So now, what are the constraints? So the constraints, like I said, the first set of constraints that we have to define is our budget limit, is the capital fund that is available to us for each year. So, and then we have to define it for each year actually. So we have 3 years planning horizon. So for year 1, the amount of money that we need at year 1 should be less than or equal to the amount of money that we have to invest in year 1 should be less than or equal to 10,015. So let me just write it this way. So constraints so the amount of money invested should be less than or equal to the capital fund available, and this should hold for each year. This should hold for year I, for year 1, 2, and 3. So we have 3 constraints to define here. So for year 1, the amount of money that needs to be invested, we get it from here. So if we select project 1, we have to put 3,000 down. If we select project 2, we have to put $2,500. But if we don't select project 2, we don't need to invest this one. So again, sum product of these numbers and the decision variables would be the money that we need for year 1. And then, like I said, we need 3,000 for project 1 in year 1. So let me just write it this way. So year 1. So the amount of money that needs to be invested is 3,000. 3,000 if I select project 1. So 3,000 times x1 plus 2,500 x2 plus 6,000 x3 plus 2,000 x4 plus 5,000 x5 plus 1,000 x6. So this is the amount of money that should be invested, and this should be less than or equal to the amount of money that is available for year 1, which is 10,500. So we need to write down the same thing for year 2 and year 3. For year 2, if we go back to our table again, here, we see that we need $1,000 if we take project 1, $3,500 if we take project 2, $4,000 if we take project 3, etc. So let me just quickly write it down. So 1,000 if I take project 1, 3,500 if I take project 2, 4,000 if I take project 3, 1,500 take project 4, 1,000 for project 5, 500 for project 6, and then this should be less than or equal to my available budget, available capital fund for year 2, which is 7,000. And then for year 3, I need 4,000 for project 1, 35 for project 2, 5,000 for project 3, 1,800 for project 4, 4,000 for project 5, and 900 for project 6. And this should be less than or equal to 8,750. And then last thing is to define the binary constraints actually. So we just need to know that xi's, I already defined it, but I need to know that xi can take only 0 or 1 for I equal to 1, 2, 3, 4, and 5, and 6 for all i's, or I could use this for all. Okay, so that's our formulation, and let's just go ahead and go to Excel to solve this. So we just need to put this just copy this, put it in here. So alternative, the list of projects. I can write down the list, but I don't need it honestly, so I can just put 1, 2, 3, 4, 5, 6, 7. There's no 7. 1, 2, 6, and then NPV for each one, and then year 1, year 2, and year 3. NPV is going to be 4,000, 6,000, 10,500, 4,000, 8,000, 3,000, 3,000, 25, 6, and then the capital funds available, 10,500 for year 1, and then 7,000 for year 2, 750 for year 3, and then 4,000, 35, that's gonna take care of our formulation. Let me get rid of that one and then bring this up. So so now I have my table ready, so I need to go ahead and so the first step to assign decision variable cells. Decision variables. So I need 6. Alternative, I need to make 6 decisions. So let's just use columns this time. So let's assign these 6 guys 6 cells for these 6 decisions that we need to make. And then for different years, we just need to make sure that the amount of money used. So before doing that, actually, let's write down the objective function. Objective function would be, we want to maximize the net present value. So net present values, sum product of these column with these column, decision variables with NPVs, list of NPVs would give us the objective function here, this one. So equal to sum product of NPVs, comma, decision variables. That's our objective function, and then we need to define 3 constraints. So I would say capital budget constraint. So we have to define it for each year. The amount of money used. So for year 1, the amount of money that we use is going to be some product of decision variables, comma, the amount of money that we use for each project in year 1. Oh, let me just put it in here. Yes. And then same thing for year 2, year 3, but since I want to just drag the formula, I want to make sure that my decision variables are locked. So I fix those guys by pressing F4 or Command T, and now I can just drag it to the right. Let me just copy the formula. It's going to be crazy bad. Okay. Just to show you the formula that I'm using. Okay, so this is the amount of money used. I'll write it here. Money invested. Money invested in each year. And these guys should be less than or equal to the money, the capital budget available at each year. So for first year we have 10,015. $7,000 in year 2, 8,750 for year 3. So that's it. Let's go ahead and solve this. Data solver. So So we want to maximize NPV by changing these 6 decision variables subject to the 3 constraints. We want these 3 guys to be less than or equal to the capital budget available, and then we had just one set of constraints, additional constraints to define, and that would be the binary constraints for decision variables. So binary, we want our decision variables to take either 0 or 1, so that's how we define it. And we have to make sure that we select simplex LP, and I assume everything is ready now. So maximize objective function by changing these 6 decision variables. We have the binary constraints, we have everything ready, so let's just go ahead and solve it. So the optimal solution, so let me just put it as part A of the question, part A of the answer. The optimal solution project 3, 4, and 6 will be taken. That's our optimal decision. Project 3, 4, and 6. So, and then the next part of the question, so that was the answer for part A. For part B, it asked, assume that only one of the warehouse expansion projects. So we have 2 warehouse expansions, a limited version and an extensive version. So if we just want, out of these 2, if we just want only one of them to be implemented, so the variable that we assign for this one is x1 and x2 for this one. So out of x1 and x2, only one of them can take 1. So this is a case of mutually exclusive. So out of x1 and x2, this is part B. So out of x1 and x2, we don't want, so if we just write it down, all the possible cases for x1 and x2 would be, they can both be 0, 1, 0, the other one 1, 1, x1 1, x2 0. So this is the set of all the possibilities for x1 and x2 for limited expansion, extensive expansion, warehouse expansion. So we can have neither of them to be selected, only extensive warehouse expansion to be selected, only limited version, both version, limited and extensive. But then it says the mutually exclusive constraint says that you won't be able to do, which makes sense, right? You won't be able to do both limited and extensive. You have to select either of them. You may do limited or extensive or neither of them, but you won't be able to take both of them at the same time. So the way, if you remember, for mutually exclusive, the way we defined this, we said x1 plus x2. We don't want this to be 2. It can be 1, it can be 1 again, it can be 0. So it can be 0 or 1, but it shouldn't take 2. So if we just put 1 here, x1 plus x2 less than or equal to 1, this will take care of the mutually exclusive constraint. And if we just look at the optimal solution, so part B, x1 plus x2 less than or equal to 1, But if we just look at the optimal solution, x1 and x2 is already less than or equal to 1. So it's right now we're not taking either of them, right? Which means that if we add this one, it's not going to change the optimal solution. But if you want to add that, mutually exclusive constraint, so we said project 1 and 2 out of project 1 and 2, only one can be selected at max, less than or equal to 1. And then the way we add it, we just go back to our solver, and then we add this one less than or equal to this one. Okay, and solve. And like I said, the NPV amount and the optimal decisions here are the same. So it's not gonna change anything because it's not gonna affect the optimal solution. And then the next one says, suppose that if test marketing of the new product, project 3, is carried out, the advertising campaign, project 4, also must be conducted. So advertising campaign, it's like these are two different phases of the same project. Advertising campaign should be done before you can test market a new product. So this one, test market a new product, is dependent to advertising campaign. But advertising campaign is not dependent to the other one. So just to put it here, so this is like a conditional constraint, and in the solution there is actually a mistake. It says co-requisite. So if you look at the solution for part C, it says co-requisite, but these are not co-requisite. So it's a conditional constraint. So project 3 and 4 again, project 3 and 4. So all the possibilities. This is the set of all the possibilities, and then project 3 was test market, project 4 was advertising campaign. Test market, advertising campaign. Oops. So we won't be able to do test market before advertisement campaign is done. So basically there's only one case here that we don't like it. We can take this one definitely. If we don't do any of them, it's fine with that constraint. If we do advertising campaign and do not do test market, this one is also fine, because advertisement campaign is not dependent on the test market, but then test market is dependent on advertisement campaign. We cannot avoid advertisement campaign and do test market of a new product. But then this is also fine. We can do both of them at this, I mean this and then this. So this is the only thing that we just want to avoid. And the way we can write it down is with so this is a conditional constraint, conditional and if we just simply say that x3 should be, if we say x3 should be less than or equal to x4, it's gonna take care of it again. x3 less than or equal to x4. All these cases can be satisfied with this linear constraint. And then, so this would be the answer to part 3. To part C. x3 should be less than or equal to x4. That's the answer to part C. And again, if we check these, if we check our optimal solution, x3 is already, this constraint is already satisfied. Both of them are already selected in optimality. So adding these constraints to the problem is not going to change the optimal solution. But then if you want to do it, so conditional constraint, and I said x3 equal x3 should be less than or equal to x4. And then we just need to add this one to our solver. Add again x3 less than or equal to x4 CF, that's okay. And if we just solve it again, you see the optimal solution does not change. So x3, 4, and 6, there's still, it's still the same as our optimal solution in part A. And that's it for this question.